Hello everyone. Today we are going to look at how abstract mathematical principles directly translate into life-saving medical technology. As you can see, we have a brain scan over here, and clearly we are talking about medical imaging. Our case study focuses on topic 5.3, inverse transformations, where we will explore a core problem in modern clinical diagnostics known as the inverse problem. And as I said just now, the CT scan. Essentially, we will discover how math allows us to decode the invisible and see inside the human body without making a single incision. So, to actually understand how this works, let's first map out the baseline relationship between a physical force and also its measure effect, as I have done here in this slide. So, in linear algebra, as we have learned, a forward linear transformation over here as Tx takes an input vector space and maps it out to an output vector space. Basically, in medicine, this represents a physical reality, what we have right now, like an X-ray, basically. And when it beams through a human tissue, and it loses its intensity based on tissue density, because different tissues have different density. So the machine actually measures that final input, which we have called here and in the slide vector y. So here lies the real world challenge. As scientists, as clinical scientists, as people over there, they can actually never visually capture the internal organs directly. We can only record the final shadows and effects hitting the detectors. Therefore, to uncover the hidden reality of the patient's anatomy, we need the linear transformation, which is T inverse y. Inverse matrix acts as our mathematical engine, perfectly undoing the forward process to trace those measured effects, as I said just now, to their original physical forms. So as I have said before, there are three logical conditions which must be met before this linear transformation rule can be applied. So firstly, the transformation must be a one-to-one, which is indexed. Every single input vector must map to a unique output vector. This guarantees no crucial data is compressed, overlapping, or permanently lost during the process. Second, it must be onto. It must be onto, which is surjective. Every possible coordinate in our target output space must actually be reachable. There can be no mathematical dead end. I repeat, there can be no mathematical dead end. And thirdly, the system must maintain a non-zero determinant. Geometrically, as we see here in the picture, if the determinant of matrix A, let's say A, equals to 0, the spatial grid collapses or flattens into a lower dimension. So this causes a 3D object into a flat line, as we can see here. So when the A is not 0, it's a non-zero determinant, the volume of the space is preserved, meaning no spatial structural data is destroyed and a perfect mathematical inverse is safely guaranteed.
Hi, my name is Pawan. On this slide, we can visualize what a matrix transformation actually does to a space. On the left, we start with the original state space. This is our original data, denoted as x. In the middle, we apply the matrix A, which transforms the space. The square is stretched, rotated, and shared into a parallelogram. This new transformed state is represented by Ax. On the right, we apply the inverse matrix. As a result, the distorted shape returns to its original square form. This demonstrates the key purpose of inverse matrix, which is perfectly reversing the effect of the original transformation and recovers the initial data. Okay, now let's verify mathematically whether our matrix has an inverse. System matrix is shown as A equals 2, 1, 1, 1. The first step is calculate the determinant. For 2 by 2 matrix, the determinant is founded by multiplying the main diagonal elements and subtracting the product of the other diagonal. Here we get determinant equals 1. Since the determinant is equals 1, it is not 0, the matrix is invertible. This means no information is lost during the transformation, therefore a unique inverse matrix exists, guaranteeing that we can always recover the original state from the transformed data. After confirming that the matrix is invertible, we calculate its inverse. For 2 by 2 matrix, we swap the values on the main diagonal, change the signs of the off diagonal elements and divide everything by determinant. So the inverse is 1, negative 1, negative 1, 2. Next, we verify our result by multiplying matrix of A, which is inverse. Performing the matrix multiplication gives us the identity matrix. This proves that by applying A, the inverse of A completely reverses the original transformation, allowing us to recover the original data accurately.
Now let's look at how computerized tomography, also known as CT scan, actually works. Many people think that a CT scanner is like a camera that takes photographs of human organs, but that's actually an illusion. In reality, the scanner fires X-ray radiation from thousands of rotating angles around the patient's body. The detectors on the opposite side do not capture images. Instead, they only measure the total amount of tissue density that the X-ray beam passes through. This creates what we call an inverse problem. We only have the final measurements, which can be thought of as shadows, but we really want to know is the internal anatomy of the patient. Therefore, we need to work backwards from the measured data to reconstruct the object inside the body using inverse transformations. So, after understanding how CT scanners collect projection data, we can see that inverse transformations and linear algebra play a crucial role in converting those measurements into a meaningful medical image. To solve this inverse problem, linear algebra is used and the process can be represented by the equation x equals A inverse B. Here, A is the system matrix, which acts as a massive geometric framework describing millions of X-ray parts through the body, while the vector B represents the measured data, which is the raw projection data collected by the CT scanner's detectors. Our goal is to determine X, which is the unknown state. In medical imaging, X represents the actual tissue density of every voxel inside the patient's body and forms the reconstructed CT image. However, in real CT systems, contain millions of rows, making it extremely large. Because of that scale of system and the presence of electronic noise, finding a perfect exact inverse metric is practically impossible. Therefore, modern CT scanners use iterative numerical methods to approximate the inverse metrics and solve for X, allowing accurate medical images to be reconstructed.
For this part, we focus on real medical situation and accurate ischemic stroke. This happens when a blood clot blocks the blood flow to a part of the brain. In this situation, time is very important because every second without proper blood flow can cause brain cells to be damaged. When the patient arrives at the emergency room with severe stroke symptoms, doctors know that there is a problem, but they do not immediately know the exact location of the clot. So, the unknown variable here is the exact position of the blockage inside the brain. To solve this, a non-contrast head CT scan is performed. The CT machine rotates around the patient and collects millions of data points from different angles. At this stage, the hospital only has the scan data, represented as vector B, but the brain condition, represented as vector X, is still unknown. Next, the raw CT data must be processed mathematically. This is where the matrix inversion becomes very important. The relationship can be written as X equals to A inverse B. Here, B represents the data collected by the CT scanner, A inverse represents the inverse matrix used to reconstruct the image, and X represents the final image that doctors can interpret. Through this reconstruction process, the system converts the raw data into a clear CT image. In the image, a bright white density may indicate the presence of a blood clot. Once the doctor can see the exact location of the blockage, they can make faster and more accurate medical decisions. This allows them to give targeted clot-busting treatment, restore blood flow, and reduce the risk of permanent brain damage. In this final slide, we can see how mathematics becomes a lens for healing. The core principle here is inverse transformation. This means we use mathematics to work backwards from the observed effects to find the hidden cause. In this case, the observed effect is the CT scan data, while the hidden cause is the blockage or clot inside the brain. Next, the tool used is matrix inversion, represented by A inverse. Matrix inversion provides the exact computational framework to untangle complex multivariable states. In simpler words, it helps convert complicated scan data into a clearer image that doctors can understand. Finally, the impact is very important. CT reconstruction is basically an exercise in solving AX equals to B. Linear algebra becomes the language used to decode the invincible condition inside the brain and make it visible through medical imaging. So, this shows that mathematics is not only used in classrooms, but also in real medical situations. Through inverse transformations and matrix inversion, doctors can identify hidden problems more accurately, make faster decisions, and help save lives.